Welcome back to AD Tutoring. In this video, we're going to begin mastering the concept of linearization. Essentially, linearization helps us approximate a function's value based off of the tangent line of a nearby point. So let's take a look at this graph to see exactly what I mean. So this is the function f of x equals x squared. And let's say we were asked to approximate the value of this function at 2.2 based off of the tangent line at x equals 2. So let's begin. Here's the overall concept. So this is the graph. I'm going to go ahead and let's go ahead and pinpoint x equals 2. Let's go ahead and zoom in a little bit. So we have 2 right here, and we want to approximate 2.2, which is going to lie somewhere right around here. And now we can clearly see 2.2. So let's go ahead and check out the tangent line of f of x squared. And there it is. So here we go. We have x equals 2. We have a tangent line drawn at x equals 2. Taking a look at 2.2, we can go ahead and approximate 2.2 because we can go ahead and take that tangent line and look at the value at 2.2. But taking a look at x equals 2.2, look at that straight line. If we were to approximate using the tangent line as we get closer and closer, check this out. Check this out. It looks like there's a very, very small gap between these 2 points. And yeah, so if we look at the approximation of the tangent line, we can go ahead and click right there. That'll give us approximately 4.8. If we look at the actual value, we see that the actual value would be about 4.84. So it looks like we were off by 4 hundredths. 4 hundredths. That's a pretty small amount, which is why linearization sometimes is a really good option to use. And so the concept of linearization, it might seem pretty inane right now, since these days we have a calculator and we rarely ever approximate. But this idea is actually really useful, with tasks like testing stability of an equilibrium point in engineering, physics, economics, ecology. This concept is used a lot. It's used very well and a lot. So, this technique, we need to get used to this idea now because it will really help us later on, especially if you intend on getting into one of these fields. So here are some common questions that you'll be asked about linearization. 1, they're almost always going to ask you to find the tangent line approximation for some function based off of a point. And when they give you the point, they'll give you the point on that function. It's usually going to be, x1, y1. So for example, they could say, find the tangent line approximation for f of x equals x squared at the point 0, 0 or 1, 1 or 2, 4, because they're going to give you a point on the actual graph. A point on the actual graph. Another question they could ask you is use the tangent line of some function, so let's say f of x equals x squared, to estimate the function evaluated at 2.2. And in this question, what you could do is you could use a nearby convenient point like x equals 2, use that tangent line, and use the approximation. And then lastly, they could ask you, is the tangent line approximation of f of a, whatever value, based off of the function. So is the tangent line approximation of f of a based off of the function at a certain point in overestimation or underestimation? And questions like these, and I'll show you in a second, questions like these are usually very easy as long as you understand concavity. Because remember, if a function is concave up, any tangent lines will lie below. If the curve is concave down, any tangent lines will lie above. All right, so just remember that. We did go over that a couple videos ago. Just make sure you rewatch if you do need to. But concavity is key. All right, so those are the 3 main questions. So what I'm going to do is I'm going to go over an example of each. That way we can get used to that, and then we'll call it a day. But first, I want to go ahead and go over the example, the last one. So let's go ahead and use the graph that we had. So let's bring it back up. Is the tangent line approximation of f at 2.2 based off of f of x equals x squared at the point 2, 4 in overestimation or underestimation? So here, if we take a look at the graph again, we can clearly see that based off of that tangent line at x equals 2, this would definitely be an underestimation because the tangent line is in yellow, or sorry, not yellow, orange. And we saw clearly that the point 2.2, 4.8 was below 4.84. So yeah, in this case, the tangent line was an underestimation. And this should make sense because this graph is concave up. This graph is concave up. And so any tangent line will lie below. And as a refresher for this, think about it this way. if a graph is concave up, this means that its derivative is increasing, or the slope of the tangent line is increasing. So this means that it should get steeper and steeper in the more positive fashion as we go up, which is true because we look at x squared, it gets steeper and steeper as we go up. And so any tangent lines, well, they won't be increasing, their slope is constant. And so that should make sense. The slope is constant, but the graph is concave up, so its slope is increasing. And so yes, it will be an underestimation because it is concave up. Up next, let's say we were asked to find the tangent line approximation for f of x equals e to the x minus 2 at the point 0, -1. So again, we want to find the tangent line approximation for this function at the point 0, -1. So now that we're doing this algebraically, we want to go ahead and use that formula that we're given. That formula that we have for linearization is f at a plus f prime at a multiplied by x minus a. And what this is essentially the formula for a tangent line. So if you were to go ahead and create the equation for a tangent line, from the very start, from ground up, you would actually be modeling this formula. So this formula is just essentially a shortcut for you to just write the equation of the tangent line. And now if you've been used to writing equations of tangent lines this chapter, then this shouldn't be so hard to grasp. So let's go ahead and begin this question. We have e raised to the x power minus 2, and we want to create the approximation at the point 0, -1. So when we're given 0, -1, this is guaranteed to be a point on f of x. So if we were to plug in 0 for this function, so f evaluated at 0, we would see that we would have e raised to the 0 minus 2, which is essentially 1 minus 2, which equals -1. So the point 0, -1 does exist, just to make sure that you know. Now up next, we want to go ahead and write that linear approximation. We can do it either way. We can use the formula that we're given to help us with time, or I'm just going to go ahead and create the equation of the tangent line for you. So whenever we create an equation for a tangent line, remember, we always have our slope, and we want to create that y-intercept, and then we're good. So let's go ahead and do so. To find the slope evaluated at 0, we can just take the derivative of f of x and then evaluate it at 0. So we have f prime of x is equal to, well, the derivative of e to the x is just e to the x. And then the derivative of -2, that's just 0, so we're good. Now we're going to go ahead and evaluate the derivative at 0 to get our slope. And so f prime at 0 is e to the 0, which just equals 1. And so if we're writing that, that equation for that tangent line, our slope is 1. So let's go ahead and just underline that right there just to make sure that we're aware of that. Now moving forward, let's go ahead and find that y-intercept now. So if we have the point 0, -1, and we have a slope of 1, we can easily find that y-intercept. We can do it by 1, well, noticing that we're actually given a point on the y-axis, or 2, we can go ahead and just write our equation for the equation of a line. We can use y minus y1, so y minus -1 or y plus 1 equals our slope times x minus x1. And if you're realizing now that this looks exactly like that linearization formula, good. So then we have x minus x1 or x minus 0. And so what we can do here is just distribute. So 1 times x, that's just going to be x, minus 1 times 0, which is just going to be 0. And then we're going to go ahead and subtract 1 from both sides to get that y by itself. So that'll be x minus 1. And so we found that our y-intercept is -1. And so that should make sense. And so here we go. This is our equation for the linear approximation of f of x at 0, -1. That is the equation. And then if you're asked, you can also complete a table of values using increments of, usually tenths. You never really go into the hundreds place unless you're asked. But, nonetheless, you can create a table of values just like the one presented here, and that's it. So if they ask you to create a table of values for the 10 nearest points, 5 before and 5 after, there you go. And so instead of saying y equals x minus 1, we could actually state that this is L of x, or the linear approximation of this function. And it would be equal to x minus 1. And we can do it just like that. Just like that. That's completely fine, because this is the linear approximation. So, next question. let's say we were asked to approximate the value of f at, let's go ahead and say 1.2. So approximate the value of f at 1.2 based off of its linear approximation. So then what we would do is, this is how we would state it. Let me go up here to the right. We would state that f evaluated at 1.2 is approximately equal to the linear approximation at 1.2. That's exactly what we would state. And so the linear approximation at 1.2, well, that is equal to 1.2 minus 1. And so that would be equal to negative 0.2. And so let's pay attention to this really quick. I stated that the function evaluated at 1.2 is approximately equal to the linear approximation, which is true. The linear approximation is equal to this, because we already stated that this is an approximation. This over here is the approximation, so the approximation is equal to all this. The function actually evaluated at 1.2, well, we have to estimate this value, so that's why this is an estimation and this is an equal sign. I hope you guys caught on to that. Because we already identified this as an approximation, we can use this equal sign. Because this was never supposed to be an approximation, because we were trying to find it based off of that, then we use the approximation sign. And if you got lost for a little bit, no worries. Just go ahead and shoot me a text, or go ahead and send me an email. I'll clarify this very, very quickly. All right, so let's go over one more just to make sure that we completely grasp this. So let's go ahead and say that we were asked to use the function f of x equals 3x squared plus 9x plus 1, and we want to approximate the value of f at 3.1 based off of x equals 3 on this function. So based off of x equals 3, we want to approximate 3.1 using linear approximation. And here's how we would go ahead and do that. Again, let's go ahead and look at that formula. The formula for linear approximation, so the linear approximation at x is equal to f of a plus f prime at a multiplied by the difference between x and a. And let me break that down for you. So the x is the actual value that we want, so 3.1. A would be that nearby point that was either given to us or we pick. In this situation, it was given to us as x equals 3. So what we're going to do is we are going to find the value of f at 3, because that's f at a. Next, we are going to find the derivative of this function at 3, so f prime at a. And then we are going to multiply it by the difference between x and a. And the reason that we're multiplying by the difference is because we have our value, so f at a, that will be that starting point. Then we will take that derivative, because that will be our slope of that tangent line. And we are going to multiply the slope by the difference between x and a, because that will give us that tiny little rise or fall. So that rise over run, that will give us that little push that we need to approximate. It'll just elevate it just a little bit. And I'll show you what I mean with the graph after we're done. So like I said, let's go ahead and do this. So if we're approximating at 3.1, this will be equal to the function evaluated at 3. So let's go ahead and do that really quick. So f of x, or f at 3, is equal to 3 times 3 squared plus 9 times 3 plus 1. So here it looks like we have 3 times 3 squared, so that's 27, because that's 3 cubed, plus 27 again, so that's 54, plus 1, that'll be 55. Go ahead and use your calculator if you don't believe me. So there we go. So that's f at 3. That is 55. And then we will be adding this. So this is our base. Then we'll be adding this to the derivative evaluated at 3. So let's go ahead and calculate the derivative. So f prime of x, well, 3x squared. So you drop the power. So that'll be 6x plus, well, 9x. That'll just be 9. And then that 1 just disappears. So we're good. So we have our derivative is 6x plus 9. And so then our derivative evaluated at 3 will be, well, 6 times 3, that's 18. Plus 9, that will be 27. So there we go. So that is our slope of the tangent line. Our slope of the tangent line is 27. And then we will multiply this slope by the difference between 3.1 and 3, or x, so 3.1 minus a, or 3. So 3.1 minus 3, that will be 0.1. So again, this is where that 3.1 minus 3 came into play, right here. And so there we go. So 55 plus 27 times 0.1. Well, 27 times 0.1. In this case, we can just move the decimal place over. So that will be 55 plus 2.7, which is equal to 57.7. And so there we go. So we can make the final statement as follows. We can go ahead and state that f evaluated at 3.1 is approximately equal to the linear approximation of this function at 3.1, which is equal to 57.7. And that's it. That's how we would use linearization. I'll be making another video with another example. That way we can get used to this idea even more. But for the most part, we can use this linear approximation formula, or you can derive your own. It really isn't that hard because it is just based off of the equation of a line. And so basically what you're doing is taking the reference point that they give you, create the equation of the tangent line, and then essentially plug in the value that you want based off of that tangent line. Or you can just use this formula, noting what x is, noting what a is, and you're good. Either way, completely fine. So go ahead and keep watching and practicing. Let me know if you have any questions or any questions that you would like me to tackle personally, and I'll be more than happy to do so. So until next time, guys, I'll see you. Keep watching, practicing, and mastering. Have fun.